Sound as a wave. Sound is created by vibrating objects. A tuning fork is an example of an object that can be vibrated to produce sound waves. As it vibrates, the prongs, these things here, create disturbances in the air which move it out in all directions. These disturbances push and pull the air molecules into each other as the tuning fork moves one way and then the other. A piece of chalk was attached to the vibrating tuning fork, so not sure how you'd exactly do it, but let's pretend it was attached right there. There's your chalk. Okay, and then it wrote on a rotating cylinder. So here's our cylinder. I'll make it a little longer, and that's rotating around. The chalk pattern looked like this. It would go up, come down, and just kind of follow that path. What conclusion can you make about the tuning fork? What's it producing? The tuning fork, the vibration of the tuning fork produced waves. And since the tuning fork also made a sound, we're going to call them sound waves. And you can click here to see a nice video on sound waves. The tuning fork produces a very clear sound that has a constant frequency. And if you have a tuning fork, well, even if you don't, you can look over there. It actually shows the frequency and what letter it is in the musical scale, like A, B, C, whatever. So, what if the size of the tuning fork changes, but it's still made of the same material? Please watch this video and state whether tuning fork A or tuning fork B has a higher frequency. Tuning fork B has a higher frequency because it has a shorter length than tuning fork A. The massive pipe organ, and here it is. All those vertical things are pipes that air flows through and makes nice sounds. The pipes perform the same function as a tuning fork. The larger pipes produce lower frequency sounds, also called lower pitch. What is pitch? Pitch is a description of how you hear a sound. An eagle screeching is a high-pitched sound. The rumble of truck tires on the road is a low-pitched sound. Higher frequency sounds are heard as higher pitches by people and animals, right? Dog whistles are a very high-pitched sound that humans can't hear. Lower frequency sounds are heard as lower pitches. And there's a relationship between intensity and frequency and how you hear sounds. And click on this video for more information. Last chapter we talked about the amplitude of waves. Now, amplitude is heard by the human ear as loudness. We have a graph here, the waveform of a sound. Way more complex than just the waves we were drawing last chapter. The graph is a waveform of a sound. The amplitude of the wave varies from beginning to end. Can you tell where the sound is loudest and where it's softest? The loudness of a sound is measurable. It also depends on how far you are from the sound source. A loud sound might not be heard very well if you're very far away. But for this graph, let's assume you're at the same place where the recording equipment took the data. In that case, over here, where the amplitude is the largest, that's where the sound is loudest, and that you'll hear it the loudest. Down here somewhere, it's the softest. And another video. Click here to see a video on sound loudness and the decibel, which is how you measure sound loudness. That's the unit we're going to use. We use intensity, right over here, to quantify the loudness of a sound according to the distance from the source. Because there are a wide range of intensities that people can hear, the decibel scale is used. It's a logarithmic scale. Not sure if you had that in math yet, but you will. And you can see what the problem is. You can hear all the way down to 1 × 10⁻¹2 watts per meter squared. Watts is a measurement of power. You can also hear all the way up to 100. That's what, 14 orders of magnitude. That would be crazy to have to kind of figure out what's going on there. If you can say, hey, I can hear something at 1 × 10⁻⁸, and I can also hear something at 100. That's because the ear hears logarithmically. So the threshold of hearing is down here. You can just barely hear that sound, but you can also hear this sound. And frankly, since you're over 135, it's going to hurt your ear a bit. So a jet plane at 30 meters sounds very much like the threshold of pain. Even though the intensity is 100 times that, it sounds almost same to you. So this is what they're going to use for sound levels, decibels, both from a mathematic point of view and also biological point of view, because that's how your ear hears. In open areas, the intensity of sound decreases with distance. The closer you get to the source of the sound, the more intense the sound, and therefore the louder it is. Sound waves are mechanical waves. Mechanical waves are defined as waves that need a medium, which is some kind of substance, to move through. If there is no medium, a mechanical wave won't propagate or move from one point to another. Without a medium, sound waves will not propagate, so they are classified as a mechanical wave. What medium do sound waves move through in your classroom or at the store? What other media do you think they can move through? Think about it, then go to the next slide for some answers. Well, in a classroom or at a store or at your home, sound waves move through the air. They can also move through walls. Many times you can hear somebody in the next classroom talking. They also move through water. But they don't move through the vacuum of outer space, since there is no medium for them to move through. This diagram shows a pipe. Okay, the pipe is the, I'll just draw it down here. That's the pipe. And then you have a moving bar at the left. You can see that in gray. And what that is doing, it's switching from pushing air molecules to the right and then pulling them back to the left. Okay, so the air molecules are the black dots. Now, focus on any one of the dots. A few have been colored red to make them easier to follow, and if you can't see the red, just try and find some other dot. They're all moving, but do any of them make the full trip from the left to the right? So let's see, there's one red dot in the middle there, here's another one, and here's the other one. No, the dots, and maybe the red dots if you can see them there, what happens? They get pushed to the right by dots to the left of them when the bar moves to the right. But then when the bar moves back to the left, the dots move back to the left. They're just vibrating to the right and then the left. Sound waves are longitudinal waves. Transverse waves, that's light. Electromagnetic radiation are transverse waves because the particles or the fields vibrate at a right angle to the direction that the waves move. But in this case, a longitudinal wave, the particles vibrate in the same direction that the wave moves. Sound waves are longitudinal waves. When you look at this picture again, you can see a wave moving from left to right. Right? You can, if you just take that mark there, then that vertical line is there. Then it's here. So that's the wave moving left to right, but the particles are just vibrating back and forth in the same direction that the wave moves. That's a longitudinal wave. We can find the speed of sound in any medium by dividing the distance it travels in that medium by the time it takes for the trip. The speed of sound varies in different media. The speed of sound is faster in solids and slowest in gases, with liquids falling in the middle. Solids have a greater density of molecules, or mass per unit volume, than liquids and gases, so the solids molecules are very close to each other. Sound waves, as hopefully we showed on the previous little illustrations, are transmitted by molecules striking each other. In denser media, the molecules spend less time traveling before hitting the next one, and that results in a higher wave speed. In addition to density affecting the speed of sound in media, so does temperature. Okay, here's air. Air's the same media, but it has a different temperature. Here's 0 degrees, and here's air, normal air, which is a lot warmer. Molecules in warmer air move faster than molecules in colder air as they have more energy. Their faster speed allows the sound wave to travel faster. And just look at some of these speeds, right? Here's gas, pretty slow, 343 meters per second, which is about 700 miles per hour. That's the speed of sound in air. And as you get denser, the speed increases, okay? And then finally, when you get to the solids here, iron and steel, 5,000 meters per second. Aluminum 5100 meters per second.